The things that cause changes in momentum are, of course, forces. Forces cause objects, or unbalanced forces anyway, cause objects to speed up, slow down, change direction, change their momentum. In fact, as Newton said, the net force applied to an object is equal to its rate of change of momentum. Now, this is actually Newton's second law expressed in a different form. This is expressed in terms of momentum instead of terms of acceleration. So the net force on an object is equal to the rate of change of momentum. So here we have that as an equation where we have mv here. Now v is obviously the final velocity, so this is the final momentum minus this mu here, and obviously u is the initial velocity, so mu is the initial momentum, and t, we're dividing by t, and that's time. And obviously the rate of change denotes the change in momentum divided by the time taken for that change, how quickly that change is happening. And when you take those two concepts and you divide one by the other, the change in momentum divided by the time, that is equal to the net or the unbalanced force on that particular object. So let's write it down in another form. F net is equal to delta P over delta T, the change in momentum divided by the time taken for that change, the rate of change of momentum. So you can see that for a larger change in momentum, or to change that momentum in a shorter time, both require a larger net force to accomplish that. So that's how that equation works, that's how it gets put together, and obviously because momentum is mass times velocity, the larger the mass of the object, the larger the net force required to make a change in momentum, etc. Okay, so let's have a look at how we use that equation. Here's a quick example here. So we have a car with a mass of 1500 kilograms, and it is increasing its velocity and therefore increasing its momentum, and that is happening in this particular time here. So let's have a look, and we want to calculate the net force on the engine. It says calculate the force required by the engine. We're assuming that's the only force, although probably it's not, but what we're technically calculating here is the net force. So the net force on that car by its engine is going to be equal to mv minus mu divided by the time taken for that change. So we're going to have 1500, I'm going to factorise here. V is 30 because it speeds up to 30 from 10 meters per second. There's no change in direction. It's going in the same direction for both, so there's no worry about the signs, and that is going to take 12 seconds. And that then is going to give us the net force. So we then have 1500 divided by multiplied by 20, which is going to be 30,000 divided by 12. And I do that on my calculator. Divided by 12 gives us 2,500 newtons. So that represents the net force on the car. And that's basically how you use this equation. Just to say that it's actually a version of Newton's second law, and we can show that because if we factorise this over here with the algebra, we get that the net force is equal to m times v minus u over t. Now, if you remember from our work on motion, v minus u over t is equal to the acceleration, the final minus initial velocity divided by the time. So we can replace all of this part of this equation, v minus u over t, with a, and that simplifies to F equals ma. And that shows us that this equation is actually the same equation as the one we previously had for Newton's second law. So just to recap, we have the relationship between force and change in momentum, where the net force on the object, the resultant force, is equal to the rate of change of its momentum. F net is equal to mv minus mu divided by t.